which I would like to do someday. All right, 10. 40 kilograms stands in one of a 70-kilogram boat.
Get the turtle.
4 meters in length, 70 kilograms. He's going to walk towards the front of the boat. Child knows the turtle 3 meters from the pier. And he is 4 meters from the turtle. Child knows the turtle and Rog, the front of the boat. He proceeds to walk to catch the turtle, neglecting friction between the water and the boat. Describe the subsequent motion of the child boat. So the child moves forward, the boat moves backward. The child plus boat system does what?
Moves back.
Stays in the same place.
Stays in the same place, no outside force. So if the center of mass, if this is being held up by a finger, the center of mass would stay exactly the same.
Okay, but in real water, you can sort of...
That's because of the friction. We said neglecting the friction in the water, which is huge, right? Because you know if you do this fast, you do have the kid going forward, the canoe going back. If you do it slowly, there's enough friction that, generally speaking, the canoe doesn't move. There you go.
Is it because they like switch places?
Right. As a kid moves forward, the boat's going to move backwards so that the center of mass stays the same. The center of mass stays the same. And we haven't actually done an equation for the center of mass yet. We will do that soon.
But vertically, isn't there a difference?
Vertically?
Yeah.
Vertically. Explain.
Like, the center of mass isn't just a horizontal.
Okay, yeah. If you're talking about this way, actually the center of mass I think would stay the same, but I'm not even talking about that.
It's different.
I'm just talking about this one here. This has to stay the same.
Yeah.
Where the finger is, it holds it up, wherever it starts, it's going to stay. Because what the canoe will, enough canoe will go backwards to counterbalance
But because the
going
canoe
forward.
is longer and flatter and heavier.
Right.
Vertically it changes, right?
Vertically, the problem is that you just count the components this way, and the canoe isn't moving at all vertically, nor is the boy. In a perfect
it's a
world.
different sort of balance you get, isn't it?
Well, if you're talking about putting a pin in another place to rotate around, yes, but we're not.
Like if you're walking with a stick and you have one of the rocks suspended up and one of them suspended down, it matters how you know what I mean?
What's
Never
the
mind, it's not.
Okay. All right. So where would the child run to the pier when he reaches the far end of the boat? So he wants to know where he is. How'd you figure this out?
I didn't get this right.
Okay. Somebody said this was easy a second
I
ago.
thought it was easy because I thought the boat was moving backwards because he's walking forwards at the boat.
That's
That's
true.
what happens in real life.
That's what happens in real life, yes. So
I
the
said-
boat moves backwards,
Would
he
he be
moves forward.
3 meters away still?
Well, no, he wouldn't be 3 meters away still. He'd move forward.
7?
He wouldn't be 7 because he'd be in the water because the boat's going to move backwards.
4?
So some random number in between. So how do you figure this one out,
I
guys?
don't know.
We're going to have a better way to figure this out later, so I will not belabor this point. But let's pick a random speed. It doesn't matter what the speed is because we know he's always going to end up the same place. He has to, right? Because there's no outside force, right? So if he ends up in the front of the canoe's going to end up backwards. He's going to the same place no matter what speed we pick. So what speed do you want him to walk at?
Wait, so if he ends up at the
2
same,
meters per second.
2 meters per second is the choice we're going to use. 2.
but if he ends up in the
That's
same
quick.
place, then why are we even doing it?
Right?
It's like a hike.
Well, he's going to move. It's just where he's going to end up. I don't know. But no matter what velocity I pick, he's going to end up in the same place, assuming there's no friction, which is a big assuming. Okay, so we're going to walk him forward. Y2.
Even
I
if
like
he moves
six.
at
I like
6,000
even
meters per
numbers.
second.
So minimum of 4 is 0. Minimum after he's moving. He's what is he?
It's not an easy difference.
He's 70. He's 40.
Wait, what if he started moving at 6,000 meters per second?
Same thing.
Seriously?
Yeah, he just gets to the front path. So 40 times 2 plus 70 times I don't know what. So what's the velocity of the boat?
80 or over 70.
80 divided by 70.
Negative 80 divided by 7.
Negative 80 divided by 70. So I get negative 1.143 meters per second is the velocity of the boat.
So why do you care?
Okay, so now that we know what the fast speed the boat is going back, we know how fast he's walking forward. How much time does it take to walk to the front of the boat?
Distance. I don't
Well,
know.
distance equation, yeah. So the distance equation is equal to 1/2 AT squared plus V naught T. The distance he's traveling is 4, but what's moving?
The boat.
Both the boat and him, right? So the boat's coming towards him even as he walks forward, right? So these two velocities would be added up. I got 1.143 coming at me, plus I've got We said 2 for the guy?
Yeah.
And then all that times t would give me how much time it takes to get in front of the boat, right?
Because there's no acceleration.
There's no acceleration. Well, again, we're assuming no acceleration. Probably a relatively benign suggestion. Whoops, I did that wrong. 3.143 equals 4 divided by shift answer, and I get the time it takes to get in front of the boat is 1.27 seconds. Agreed?
Yeah.
Mm-hmm.
1.27
We're doing
seconds.
all of this relative to the shore.
Yes.
When we could be doing all of it relative to the boy. And then.
Well, it'd be very tricky to do it relative to the boy because he's changing reference frames.
But he's shuffling the boat under him.
Right.
Towards it. No, maybe.
Right. Now, I'm not
It seems like
disagreeing.
it'd be easier.
What would happen is you could do the boy that way, but then you'd have to figure out how far the dock moves because now the dock's in a different reference frame. Which it's okay, you can do that. It's just that's the way most people's brains would melt a little bit. And to be frank, we're not going. After we do rotation, there's no way you're going to do the problem this way. There's no way it's going to do the problem. It's not going to happen. Okay. They said, well,
How are we gonna do it?
you would. Maybe you would do it a different way. Be interesting to see. But anyway, we got how many seconds, right? Because one of us was worried a little bit straight. So we know that's there. So how far can the boy walk at 2 at 1.27 seconds? How far does he walk in relative to the dock?
4.5.
So what?
No. Sorry.
He's moving at 2. That's his
2.5.
time.
2.
I get 2.54 seconds. Sorry, 5 meters. And he started at 3 away, so now he's 5.54 meters away from the dock. See, will he catch the turtle?
No.
Nope.
Thank God.
The turtle is
Also,
safe
only snapping turtles.
from his predations.
Really
Snapping
know
turtles
sex.
can jump like 5 feet.
Yeah, snapping turtles are terrible.
Snapping turtles can jump 5
They,
feet.
I'm not even kidding, Resy. It's the scariest thing.
Not a
ever.
biology teacher, but I
Wait,
find
we
that
should actually-
impossible to believe.
Let's look up a video of a snapping
Yeah.
turtle.
I'm not
No.
talking like
Snapping turtle.
there's different
Remember
types of
DC
snapping
snapping
turtles.
turtles?
The
Mitchell?
ones that my cousin.
Remember DC snapping turtles?
Yeah.
I'm not kidding.
Why would an elementary science
Turtles have always
teacher have
freaked me
snapping
out.
turtles in his room and encourage kids to play with the snapping turtles?
We had a turtle as a
It
pet.
was
in kindergarten.
messed up.
Wait,
Yeah,
have you
rats
ever
made
what?
snapping
And they
turtles.
were always like, it's your turn to clean it. I was like, I'm not touching that.
Have you ever taught biology?
No,
Are you licensed?
I'm not licensed. Not licensed.
Why not?
Because I would
Because
need
it's
a whole other
learning.
year of biology, and I didn't like the first 2 years I took.
Like you were already
But
that
then,
far.
did you take lots of chemistry?
I took lots of chemistry.
No.
You only need 2 years of chemistry to teach chemistry at the high school level. You need
That's
3 years of
shocking.
biology.
How many years?
How many years of physics?
No, only 2 years of physics to do it.
7.
Took a whole lot of extras.
years.
Yeah, but you're taking them at the same time. It's going to be take. Never mind. 2.
Like you just need one class. for
Well, it
2
depends.
years.
I mean, it also depends what state. Each state licenses you differently. Each state licenses you differently. Okay, you said you needed 2,
Yeah.
Yes.
so my disappointment's growing.
I
No, I set this one up.
I got a bullet. The bullet's traveling 400 meters per second. Is that right?
Yes.
Let's look at the picture.
Actually, I can probably figure this out now that we did the other one.
1 kilogram is in the block. The block's initially at rest on a frictionless horizontal surface connected to a spring constant of 900 newtons per meter.
Oh yeah, the spring messed me up. I didn't know.
The block moves a distance 5 centimeters back, which is 0.05 meters in real physics land. Find the speed at which the bullet emerges from the block and the energy lost in collision. So, since it says energy lost, we're not going to do an energy problem. What kind of problem are we doing here? Momentum. So we're going to momentum before, momentum after. Momentum before is mass of the bullet, 0.005. Velocity of the bullet, 400. Momentum after. Momentum after.
Well, the block would have a
Yes, the block is a mass. Is that a mass?
Yeah, one.
Okay. So it's got 1, but we don't know its velocity. That's a bummer.
And then are we assuming the bullet is at rest?
No, it's still moving. It went through the block. So we've got 0.005 times velocity of the bullet, right?
Okay.
So that is a not happy place to be, because we have two unknowns.
And then we go energy. And that's
So
where
then we're
you
gonna
bring
energy
in
before.
spring.
Energy after. So I've got 1/2 mass, the velocity of the bullet was 5 times the velocity of the bullet, which was 400 squared, equals 1/2, don't know the velocity of the block still, squared, plus 1/2 point,
Don't you have to bring in the spring?
oh yeah, plus the energy of the spring.
Why do you have to do that?
Oh, actually, if you want to, we could drop the velocity of the block if you want to,
Why?
because these aren't at the same time, right? One of them's happening when the bullet goes right through, and the other one's happening
After.
afterwards. The spring doesn't coil until the velocity of the block is 0 again.
So
Right.
you have to drop it? Or
So
you-
one of these two has to be dropped.
Block.
That's
Yeah.
the velocity of the block.
That's how I set it up.
Not the best choice, but we'll do it.
Wait, no, that's like that's the worst choice you can
Yes,
do.
that is the worst choice. We'll keep going. All
Oh.
right.
I
Plus energy lost, right? Energy lost. So I just added a whole bunch of unknowns.
No, no.
No, but
They help
energy
me all.
of the spring we have.
We have it.
We have that spring.
1/2 kx squared.
And how much do you have? Do you have the distance it went?
Yes.
Now, the energy before for the spring was what? What powered the spring?
0. Oh, what?
What powered the spring? Something compressed it. What compressed it?
The
Bullet moving through the block.
The bullet did not power that block, that
Block.
spring. Disagree. The block did, right?
But the bullet powered the block, so technically the bullet powered the spring.
Yes. So 1/2 1 times v squared of the block, which by the way is the same v as this one, right? Is equal to the 1/2, what's k?
900.
X squared. So I can solve for the velocity of the block after the bullet hits it, right? So let's do that. I don't know what my calculator is.
I'm gonna run out of the
This is
room.
too much. It's hard. I don't want.
Is our test gonna be a lot of these problems?
It's a little hard to describe, but not
No,
really.
it's the AP test question, so
Yeah.
like this.
If you can handle these, you should be able to handle those, whatever the AP throws at you. I got 1.5 meters per second. Any chance that's right?
Is the velocity of the block after?
So
So
that's the
now
velocity
that
block
we have
after the bullet
that,
passes through it, right?
plug
But
it
before it
into
powers the
momentum
spring,
one.
right?
I'm not.
So now I can figure out what the velocity of the bullet is, can't I?
Yeah. So the energy lost in the collision, how do we do that?
Well, once I have that, then I can figure out the energy lost by using this expression here, right? Because we'll have the velocity of the bullet. We'll have the energy of the spring, which you just gave me right here. Energy lost.
Okay.
Okay, so times 1 makes sense. 0.005 times 400. Oops, that's 4,000. One of those. Minus shift answer.
That's probably
Divided by 0.05. I was back in there again. That's great. So the velocity of the bullet I have is now 100 meters per second. Is that right? And if it's 100 meters per second, now it goes into here. And we can solve for the energy. We have the energy of the spring, which is this one here. We'll find the energy lost.
Jeez Louise.
Make sense?
Yeah, it does. So we always have to use for these problems momentum before equals momentum after and energy before equals energy.
Could be.